Hey guys, so yesterday you did a lab learning about the relationship between voltage, current, and resistance, a concept known as Ohm's law. Today we're going to review those terms and talk about what you should have learned from the lab. So first we're going to talk about electric potential and potential difference. So last unit we talked about the term electric potential. We used the symbol V for electric potential. And electric potential is the electric potential energy of a charge divided by its charge, and that's measured in volts. And then we're also going to talk about a term called potential difference, which is very similar. So electric potential is a value that you only have at one certain location, and potential difference, as the name implies, is the change in that value from one location to another. Alright, so as you can see, the symbol V is also used for potential difference, although some people use delta V to show that it is a change. And so both of them are measured in volts. One is really just talking about a value compared to some other place that has a value of 0. That would be electric potential. Whereas potential difference is really talking about the difference between the electric potential at point A and point B. So let's take a look at an example with a common battery like a AA battery and a light bulb. Alright, so we would say that this battery provides a potential difference of 1.5 volts. And the reason for that is that the electric potential at the positive terminal, called the cathode, is 1.5 volts. And at the negative terminal, the anode, we have an electric potential of 0 volts. So the potential difference from the cathode to the anode is 1.5 volts. Now in a circuit, what's really moving is electrons, and so what happens if I put an electron right here by the negative terminal, that's where it's going to have the highest potential energy. It's going to be repelled by the negative terminal of the battery, and that's going to push it through the light bulb and over to the other side of the battery, and that's where the energy in a battery comes from, is from that potential difference. So if you remember from last unit, the electric potential energy should always equal the charge of the particle times the potential difference, or the voltage at which that charged particle is. So let's figure out how much energy there is for an electron at the negative terminal of the battery. So if you remember, the charge of an electron is 1.6 times 10 to the negative 19th coulombs. And it's across a potential difference of 1.5 volts. So if we calculate the electric potential energy of the electron at that negative terminal, it comes out to 2.4 times 10 to the negative 19th joules. Now that's not very much energy, but as we'll see in a minute, lots and lots of electrons are going to get pushed through that light bulb in a pretty short amount of time. Alright, so the other variable in your experiment yesterday was current, and current is defined as the rate of charge flow through a conductor. When we measured current, it's measured in ampere, which uses the symbol A, and people often will say amps instead of ampere. And 1 amp is the same thing as 1 coulomb per second. So if we want to calculate the current going through something, it's a very simple calculation. It's just that I, the current, equals delta Q, which is the amount of charge that flows through a conductor, divided by T, the amount of time that it takes for that charge to flow through. So let's look again at our example of a battery and a light bulb. Alright, so as we were talking about earlier, electrons want to move away from the negative terminal of the battery and towards the positive terminal of the battery due to the potential difference. Now that's going to be true for an electron that's right here, but of course that's also going to be true for the electrons that are all throughout this circuit, because this circuit is made of metal, and each one of those metal atoms have electrons in them, even these in the filament of our light bulb here. And so what's going to happen is when we connect this circuit, all of these electrons are going to repel away from the negative terminal and towards the positive terminal of the battery, even up through the filament here. And they're going to all start working their way around that circuit in a counterclockwise direction like you see. And so lots and lots of these electrons, all of these free valence electrons in the metal, will be moving at the same time, and so what we'll get is a counterclockwise flow of electrons. But the definition of current was invented a long time ago, before we even knew what electrons were, and current was defined as positive charge flow. And so even though the electrons would be going in the counterclockwise direction, as you see there, we would actually describe this current as flowing in the clockwise direction, because we describe current as the flow of positive charge. So while what's really happening is electrons moving in the counterclockwise direction, we would still define this current as being in the clockwise direction, because that's the direction of positive charge flow. Now the nice thing is, whether we think of this as positive charge going in the clockwise direction or negative charge going in the counterclockwise direction, the effect is the same either way, so it doesn't really matter. So once again, just to recap, for this circuit the actual current would be electrons flowing in the counterclockwise direction, but we would describe this current in terms of conventional current, which is positive charge flow, which for this circuit would be in the clockwise direction. So let's try a calculation with current. Alright, so for this problem we want to know that in 5 minutes how many electrons are going to pass through a wire with a current of 0.25 amps. So the first thing I'm going to do is write down what I'm given and what my unknowns are. So for this problem, I'm given that the time is 5 minutes, which I've converted to the standard units, which is 300 seconds. The current's 0.25 amps, and I'm going to solve for how much charge passes through that wire, and then I'm going to convert charge into number of electrons. So the first thing I'm going to do is write down my original equation and rearrange it for the unknown. So as you can see, I've written down that I equals delta Q over T, multiplied by T to solve for delta Q, which equals I times T. So for this problem, all I need to do is multiply 0.25 times 300, and what that's going to tell me is that 75 coulombs of charge would pass through the wire during 5 minutes of time. Now what I'm going to do is convert 75 coulombs into electrons, just like you learned how to do last unit. So I've taken 75 coulombs multiplied by 1 electron for every 1.6 times 10 to the negative 19th coulombs, and that tells me that 4.69 times 10 to the 20th electrons would pass through that wire in 5 minutes. So as I said earlier, a whole lot of electrons are passing through that light bulb that we were talking about in the previous problems. Alright guys, so in the lab yesterday, you varied voltage from trial to trial through a resistor, and then you measured the current passing through that resistor. And from your data, you should have made one of two graphs. So for the lab yesterday, you may have made a graph of current versus voltage, as you see on the left here, and that would make sense because you guys changed the voltage from trial to trial and measured the current as a response to that. So a lot of you may have put the independent, the voltage on the X, and the dependent on the Y, and if you did that, you should have seen a graph that looked a lot like this. But some of you may have made the graph the other way, and if you made this graph of voltage versus current, you should also see a graph that looks like this. The only real difference is on the graph on the left, you should see a very, very small number for your slope. And on the graph on the right, you should see a much larger number for your slope, something in the hundreds, probably hundreds, 200s, 300s, something like that. But what's really important here is whichever graph you made, you have a straight line, you have a positive slope, and you have a y-intercept of 0. So either one of those graphs show you that your current is directly proportional to your voltage. So if we focus on the graph on the right and we calculate the slope of this graph, the slope of this graph is something called the resistance of the resistor that you were using. Now if you use the graph on the left, that's okay too, because this slope would just be the reciprocal of the other slope. So this would be 1 over the resistance. So either way, we can derive a real famous equation known as Ohm's law. So on the graph on the left, we put current on the y-axis. Our slope, we said, is 1 over r. And on x, we have the voltage. And our y-intercept was 0. On the graph on the right, we put voltage on the y-axis. Our slope is equal to our resistance. and we had current on the x-axis, and once again our y-intercept was 0. What you will see is that both of these equations simplify to Ohm's law, which is that V equals I times R. So the potential difference across a conductor will always equal the current through it times the resistance, and that is a famous equation known as Ohm's law. Okay, so the last thing we're going to talk about today is what is resistance. And once again, the symbol for resistance is an uppercase R. But resistance is the opposition that a substance offers to the flow of current. So basically, the higher the resistance of something is, the more of an insulator it is. And the lower the resistance of something is, the more of a good conductor it is. Resistance is measured in ohms, which is the Greek letter omega. Looks like an upside down horseshoe. I don't draw it very well. And 1 ohm is the same thing as 1 volt per amp. And to me, if we rearrange Ohm's law and solve it for resistance, we can quickly see what resistance really is. It's the voltage divided by the current. So if you put a lot of potential difference across a substance and a very small amount of current goes through it, that would mean that it has a very high resistance. But if you can put a small amount of potential difference across an item and a large amount of current goes through it, that would mean the resistance of that object was very, very low. So it's really just the ratio of the voltage to the current for any conductor. Now let's try a problem involving Ohm's law. Alright, so for this problem we're dealing with a 100-watt light bulb. Now 100 watts refers to the power. Of course you guys know watts measure power from previous units. And you'll learn how to calculate electrical power a little later on in this unit. We don't really need that number for this problem though. What we do need to know is that it has a resistance of 144 ohms and it's plugged to a standard wall outlet in your home, which is 120 volts. And we want to know what is the current going to be through the bulb. So let's write down our givens and our unknowns. Alright, so as you can see here, we're given our resistance of 144 ohms and our voltage of 120 volts, and we want to know what is the current. So let's write down our equation and let's rearrange. Alright, so Ohm's law says that V equals IR, so I then would equal V divided by R. So we can plug in 120 volts divided by 144 ohms, and what we will see is that that gives a current of 0.83 amps. So 0.83 coulombs go through that light bulb every second. Now a standard wall outlet actually produces something called alternating current instead of direct current, which we'll talk about next week, but the equation still applies. Alright guys, see you guys on Monday.